All right. So hopefully today is some review. We're going to go through electron configurations, like in great detail, talk about the data behind them all and the usefulness of them. The reason we emphasize electron configurations is because you can't understand atomic spectroscopy without them. So all of the energy levels are labeled using term symbols, and the term symbols are based upon the electron configurations. So we got to go through and look at the construction of the electron cloud. And remember, these are wave functions, and so let's look at the different waves that are involved. So just like we had the particle in a box with the wave, and it was in a single dimension, you pluck that string and it vibrates up and down. There's an imaginary plane, so it's really kind of rotating. That's why it interacts with light that has angular momentum. And so we have these quantum numbers. Well, in the 3D wave mechanics, the electron cloud is like this oscillating shell or electron cloud. It's shaking certain ways. And so we can have an s orbital with L equals 0, the angular momentum quantum number. And look carefully at the colors here as we show this oscillating. So it's going to expand at some point, and then it's going to contract at some point. Oops. And so it's oscillating out in all directions. So when we draw an s orbital, we really just shade it or not shade it. The whole thing is the same color because the whole thing is expanding in all directions or shrinking in all directions. So that's what we mean by an s orbital being the same color all over. The colors are expanding and contracting. So sometimes we'll put plus or minus on them, and we're not talking about charge. We're talking about whether it's expanding at that point in time or shrinking at that point in time. Now this is the angular momentum quantum number, and so it has 0 angular momentum, meaning if you look around there, the wave doesn't seem to be rotating around the nucleus at all. Okay, it's just oscillating out in all directions. Whereas the L equals 1 quantum state or angular momentum quantum number, this one is oscillating up and down, but just like the imaginary plane on the string, where it's forward and back. So the particle in the box is oscillating up and down like this. The imaginary plane is oscillating forward and back. And so it looks like it's rotating. If it goes +1 real, +1 imaginary, -1 real, -1 imaginary, then it looks like it's rotating and it has 1 unit of angular momentum. The p orbital, likewise, the imaginary plane can be imagined as left and right. And so it's up, left, down, right. So it also has 1 unit of angular momentum as it goes through. The L equals 2 has 2 units of angular momentum because it's going out in 2 spots, okay? And it's squished in those other 2 spots. So the red is showing how it's squished in, and the green is showing how it's pushed out. And now there's 2 parts that are rotating. It's almost like there's 2 particles rotating. It's not 2 particles, but there's 2 parts to that wave function that are rotating. So it has 2 units of angular momentum. And so this is what it would look like. And so it's kind of like this green part has rotated down here. Now this one is rotated down here, and it repeats. And so that's why we talk about these as having angular momentum, even though you really don't see anything spinning. You can kind of look at the positive regions and see how they spin around. And so we have all of these. You can see as they increase in angular momentum, they have more and more parts that seem to be spinning around. Okay. Only certain ones are pretty easy to see the sort of spinning nature, if you want to think of it that way. Let's just look down this first column. It's pretty easy as we go down this column to see that green, if there's an imaginary part here, it would move to the right 90 degrees, and then it would move to the back. Whereas this one, the screen would move back. There's 2 of them moving, and here there's 3 of them moving. And then in the F orbital, there's 4. So you see the F orbital has 4 units of angular momentum. So as that blinks from purple to green, it would look like those 4 parts are rotating around, yeah. Okay. And so these are the shapes of the s, p, d, f, and g orbitals. and it goes H, I, and so on. It gets even higher. And you can see all of the M sub L quantum numbers. We talked about these last time. And so that the N sub L's are bound by L. So if L equals 4 for the G orbital, you have minus L is negative 4, plus L is 4, and then it's all the integers in between. So we just work our way up from the minimum to the maximum, and that's how many we have. So you can quickly calculate if we have negatives and positive plus 0, the degeneracy is 2L plus 1. So 2 times 4 is 8, okay, plus 1 is 9, so we should have 9 of these, and we do. We have 3, 6, 9 of those. So what about this one? 2L plus 1, 2 times 3 is 6, plus 1 is 7, so we have 7 M sub L's. Here, 2 times 2 is 4, plus 1 is 5, and so we've got 5 d orbitals. So that's the degeneracy of each of those types of orbitals. We looked at the different shapes, so these are the p orbitals. We typically put those in the Cartesian plane of px, py, and pz, and then we have the d orbitals. And so we have we looked at last time the x times y, the x times z, and the y times z. They all have that plus minus pattern going around the 4 quadrants. And so you should recognize those. They have the same pattern with the dx squared minus y squared, but they're along the axes. You see, they go right along the axis. But it's the same shape. And then the one unique one is this 2z squared minus x squared minus y squared. That's the one with the little donut in the middle. Notice those other orbitals have that version, but you end up with 2 donuts on the f orbital and 3 donuts on the g orbital. So it's kind of strange. I don't even know the functions for those. I've never seen them written in terms of Cartesian coordinates or anything like that. So if you wonder what those are, I do too. I'm sure we could Google it. It's out there. But we only go through the d orbitals, and so we'll just be happy with that. Is that cool? All right, so then we talked about the energies, not depending upon the angular momentum quantum number in 1 electron atoms, but when we get to multi-electron atoms, we have these situations. And then we ended here with electron configurations in the last lecture. So let's do oxygen. Let's finish this list here. So let's build it up. That's what the Aufbau principle means. Aufbau means build up. You're going to learn some German in this class. And so oxygen, we look up there, we see that it has 8 electrons. Okay, so we put 2 here, 1, 2, and then we go up to the next one, 3, 4, and then here, let's pay attention. Hund's rule says we put them all spin up first before we start pairing them. So Hund's rule So I'll just simplify it. Unpaired first. So you put them in the orbitals unpaired first. So we did 4. So we got 5, 6, 7. So you see how we put all of them up. So that would be the electron configuration for nitrogen. We have the 3 electrons in the p orbital. But then with oxygen, we have 1 more. We have 8. And so we've got to pair 1 up. Now, it doesn't really matter which one you put that electron in, because we're dealing with electron configurations. A permutation is a microstate. So we put that paired electron in the first orbital, let's say m sub L minus 1, or in the middle one, m sub L 0, or the right one, m sub L plus 1. That's 3 microstates. And they, at this point, have the same energy. They'll be slightly different in energy, but at this point, we're just drawing them with the same energy. Okay. And so we could look at this. We have 1s2. So when we say 1s2, that's what we mean. There's 2 electrons in the 1s orbital. Then 2s2 and 2p4. So that's the electron configuration for oxygen. Okay. Let's skip over chromium and do manganese first. And so for manganese, we're going to look at that. It's right there by iron in the middle of the D block. We're going to go back to the previous noble gas, because why write 1s2, 2s2, 2p6, 3s2, 3p6 We're going to just wrap all of that up and call it an argon core. And then we come into the periodic table on row 4. So it's 4s. And we're past that. You see, manganese is past that. So we're going to go ahead and fill up the 4s with 4s2. And then we count in the 3D block. 1, 2, 3, 4, 5. So 3D5. So that's the electron configuration for manganese. The reason I held off on chromium is because it's an exception to this rule. We can look at chromium, and it could be this. Okay. But notice I've got an open seat here, and I'm filled up here on the 4s. So I'm going to take this electron and I'm going to move it out here and put it in the 3D5. So the 4s1, 3D5, notice all of the spins are up, so that's Hund's rule. So Hund's rule loves that. High spin. So Hund's rule likes high spin situations or high spin states. And so that's nice. Now, what do I mean by better? So why is it better? Remember, I've been really struggling with trying to figure out a way to explain this to you guys, because otherwise it's just an exercise in memorization. Raise your hand if you know anything at all about music. You play a piano or an instrument or anything. Raise it high so I could see. Okay, a vast majority of the group understands something about music. Have you ever heard of a chord? Okay, and have you ever played a wrong note? Okay, a wrong note's not in the chord. Okay, and so you can add certain notes. You know, you can play C, okay, and you add a G, and that's a fifth, and it sounds nice. Okay, you add an E, and it sounds a little better. Okay, you've got a chord, the first three notes in the C chord. You add that top C, and it sounds very nice. Okay, and so remember, we're dealing with waves. So the chord is the whole electron cloud. And there are certain coordinations or combinations that sound better than others. So the whole chord is better if you have all the notes. And so that's a way of thinking about how if we can move that extra electron from the 4s over into the 3d5, we've got a more perfect chord. And the whole atom drops in energy. So that's what makes it better. It's really about energetics. It's not about sound. Okay. But the idea that you could have an incomplete chord where you got a 3D4, but a 3D5 is better and lower energy. So it's really about the energy. But why does the energy lower? That's more of an interaction of all of the waves with each other. And that's more of a chord analogy. So it's not a perfect analogy, but it hopefully gets your idea of thinking about the resonance of the whole cloud together. And that depends upon how the electrons are in all of the orbitals. So here's all of sort of a nice picture of the periodic table with when I talk about the different blocks. I talk about the P block and the D block and the F block. This is what I'm talking about. So down here are these ones that are pulled off to the side. That's the F block. Okay, 4F and 5F here. This middle region is where we're filling up the D orbital. So that's the D block elements. These are the main groups. The S block and the P block are what we call main group elements. Okay. And so you should be able to like easily look this up. You see, okay, molybdenum right here. You know, I'm 4 into the 4D block. So I'm going to have whatever core I had, the krypton core, 5s2, 4d4. So I should be able to walk my way through the periodic table with any of these. Yes.
Isn't that an exception, like well,
Okay, it would be, yeah. But I just was walking my. I picked the bad one. Niobium. Okay, 4D3. Yeah. Quick thinking. Yeah. Questions? Okay, so this would be a great way to look at the periodic table, see the electron configuration blocks. Yes.
Well, what about the one before 3?
The 3, it won't move that far. Yeah. So the chord's not that much of a draw. So we're talking about slight differences in energy. And so all it takes, I mean, like we get close enough with the D4 to go ahead and the energy will drop a certain amount with that D5, but it won't drop too much. So if we go from say right here a vanadium and it steals all both of those 4s electrons to get D5, that would drop it some, but not as much as if we had a 4s2 and a 3D3. So it doesn't drop it below that. Remember, we're talking about the energy of the whole atom. And so it has to be close enough for the atom to drop below the normal mixture of electrons in their orbits. Okay. Does that make sense? If you get close enough, what's close enough? Well, D4 is close enough. D3 is not. And also D9 is close enough. So copper is very close to D10. So it'll steal a 4s electron. And so it'll be 4s1, 3d10 for copper. Yeah. So it's close enough. So one away from being fully filled or half filled is close enough to steal an s electron.
Is that here?
Yeah, yeah, yeah. And so here's the evidence for all of this. Okay. And so here's a little symbols like don't go to the F block. Because it's kind of a wild west in the F block. We'll do some F block ones. We'll understand them in terms of like what science has given us, but we might not understand why. Like it's some really weird stuff. And so I'll show you one of Mercury, which is just absolutely crazy. The ground state of Mercury is inexplicable to me. Okay, so we'll just go with that. But look at these little weird exceptions. Well, first of all, do you see some trends? What do you see in this table? Let me see what you see when you look at this. This is the first ionization energy. So it's the cation. So we're missing an electron in the cation stay in the neutral. So how much energy it took to strip an electron out of this atom. So that's the energy difference between the neutral and the cation. So which element is the hardest to ionize? Helium. You can look at this chart and see helium is the hardest one to ionize. And it's got a S2, one S2. So paired electrons, very stable neutral, and very far apart cation. So that arrow is the longest. Okay. What about the easiest? Let's see. This looks like probably cesium. So that's the easiest one to get an electron off of. So it's that 6s electron. It's easy to steal that electron. Remember that sodium was as big as Texas. Okay, if the nucleus was in front of target. Okay, and so who knows where the cesium electron is? Way out there, middle of the Pacific or something. But we see some funny business. You see some trends, like see from sodium up to argon. There's a trend. It gets harder and harder to ionize as you go towards the noble gases. The noble gases are really hard to ionize. That means they're not very reactive. Okay, but we see some funny little monkey business here. We get to this fully filled shell, and then it's easier to pull an electron off of aluminum than it is off of beryllium. Yeah, no, magnesium. This is beryllium. So we see these little wiggles. So let's explain these wiggles and look at them. Here's one beryllium to boron. There's a little jump. There's also this wiggle at nitrogen to oxygen, magnesium to aluminum, and zinc to gallium, and so on. So we're going to look into all of this data today. And so this is the copper situation. So Gary's very happy with his 2 electrons as a 4s orbital, and copper comes along and says, I'm a 3d9, give me one. I like that one. I watched Tom and Jerry as a kid. It was awesome. It's a great cartoon. Okay. So these are the trends that we see. The first ionization energy decreases with the size of the atom. We saw that with cesium being a huge atom, much easier to ionize than either hydrogen or lithium. The first ionization energy increases across a row of the periodic table. So we went from sodium to argon. You saw it go up. So sodium was low, argon was high. So as we go across the row on the periodic table, it gets harder and harder to ionize. Now, why is that? Well, we're adding a proton and an electron with every march to the right. So we add a proton, we add an electron. But remember, especially think of the p orbitals. If I'm a p orbital and this is the nucleus, if I'm oscillating this way, I've got an independent view of that nucleus. Now we add another proton and another electron. Okay? We add another proton, I'm even more attracted to it. And the other electron is in a different orbital. So it's not interfering with my attraction to the nucleus. So it's out of my way. So I'm drawn closer to the nucleus, it's drawn closer to the nucleus. We add another proton and another electron. Now this one's above and below the nucleus, doesn't obstruct my view at all. And yet I've got a whole nother positive charge, I'm drawn even closer to the nucleus. So every time we add a positive charge, all the electrons are drawn closer to the nucleus. And the other electrons don't really shield much of the nucleus from me. So as we add electrons and protons, the protons, extra protons, hold or draw those electrons in and make it harder to ionize. And then it's some unusual, these next three trends are the unusual things we see. We see these little wiggles in the data. The first two trends are the macroscopic trends, and then the third, fourth, and fifth trends are unusual. Trend 4 is unusually high from half-filled subshells, and then trend 5 is unusually low from a subshell with only one electron in it. So one electron past a fully filled subshell. So let's look at these individuals. So this first one, the first ionization energy decreases with the size of the atom. So you can see this here going from helium to radon. Even in the noble gases, you see the first ionization energy decreases as you go down the periodic table. Because going down the periodic table, you get bigger and bigger atoms. So radon is actually easier to ionize than all of these other atoms above that. Like it's easier to ionize than hydrogen, actually, if we were to draw this line straight across. See, hydrogen is harder to ionize than radon because radon is so big. It's a noble gas, but it's more reactive than hydrogen in terms of its ionization energy. And so here, helium, what we're doing is we've got the 1s electrons in helium, and then the cation. This is the first time I guess we've seen the electron configuration of the cation. So you can look at helium, it's 1s2. If you take an electron away, you got 1s1. And here radon is 6p6, and the cation is 6p5. So we pulled an electron out of that last p orbital. Okay, across a row of the periodic table. So all of these zigzags that you see, those are the rows in the periodic table. Hydrogen to helium, or lithium to sodium, or neon, sorry, sodium to argon, potassium to krypton, rubidium to xenon, cesium all the way over to radon. Look at mercury. Mercury is almost as good as a noble gas. It's pretty far up there. And so here's the interesting thing. So lithium has that extra electron in that s orbital, and if you take it away, then I have lithium cation. So got a noble gas configuration. If I've got neon, that's hard to do. I've got here a noble gas configuration, which is like a perfect chord. And I'm taking away one of the notes. I'm ruining the chord by making a cation out of a noble gas configuration. So now we'll really get into this idea of this perfect chord being broken. Here we have the fully filled subshells. Okay, so these are, even in the middle of these groups, fully filled subshells. So that's a fully filled s orbital here in beryllium and magnesium. And then zinc and cadmium are fully filled subshells. You see how those are pretty high, and then the next one is really, really low? So I've drawn some dashed lines to kind of show the improvement because it's a perfect chord. So the whole atom, when you get to 1s2, 2s2, you have fully filled subshells. The neutral has dropped in energy because it's all resonant. It's all beautiful, right? Sounds great. And so what we want to do is we want to see where this little dashed line is. Whenever we have a perfect chord, we see a stabilization of the whole atom. So here the neutral is stabilized. What is that arrow going to do when the neutral is stabilized? If it wasn't stabilized, the arrow would be this long. But because it's stabilized, the arrow is longer. And that arrow is the ionization energy. So the ionization energy goes up when you have a perfect electron configuration in the neutral, the ground state. Okay, what about this one for boron? See, look here at boron. It's a little lower than you would expect. It should be higher than beryllium, but it's not. It's lower than beryllium. That's because when you ionize it, the cation has a fully filled subshell. That's a perfect sound, okay? It sounds nice as the cation. Well, if the cation energy drops, what happens to the arrow? It shrinks, okay? So if you stabilize the cation, it's going to be easier to ionize. If you stabilize the neutral, the lower energy level drops, then it's harder to ionize. So this is how we're getting these conclusions that the fully filled subshells are stable, okay? And so here's the neon one. Again, this one right here is stabilized. So when you stabilize the neutral, this arrow gets longer, and neon is harder to ionize. Okay, the same thing can be said about half-filled subshells. So the data related to this is nitrogen and phosphorus, and to some degree arsenic. So we see right there halfway across the p block. This one is again so prominent because those p orbitals have independent access to the nucleus on the x, y, and z axes. And so here we have the half-filled subshell, the 2p3. That's that magic chord. Okay, perfect sound. And it's in the neutral. So it drops, making the ionization arrow longer. And so that's why nitrogen is so high. Whereas oxygen is one past that. And so you see the cation has the 2p3 in it. So because the cation is stabilized, oxygen is lower than we expect. This arrow is shorter than we expect. Okay. So this is the data that tells us that half-filled shells are stable. And then we go past the subshell that's filled to form a subshell with only one electron in it. Okay, so these are locations like all of these, the lithium, boron, sodium, aluminum. Like look at boron. Boron is one electron past, so boron's over there, one electron past the 2s2. So it's just got one electron in a subshell. It'd be real easy to pull that out. And so that's what we see. If we've got boron, if we can get rid of that extra electron, we form a really stable cation. So again, if the cation is stabilized, then the arrow is shorter than you expect. And it's easier to ionize boron than it is to ionize beryllium. Same with lithium. There's a noble gas configuration up here, just like helium, 1s2. So again, that stabilizes the cation. and makes this arrow shorter than you would expect from the typical trends. Oxygen is 1 electron past a half filled. So see, it's 2p4. If it can lose an electron, it becomes a 2p3. And that means that the cation is stabilized, which makes it easier to ionize. So now let's look at if we're ionizing something, that electron comes from the s orbital for the d and f block elements. So this is interesting for these d block elements here and for the f block. When we ionize that, we lose an electron from the s. So let's do an example for let's pick iron, okay? Iron. So iron is argon core. And then we come in on the 4s, 4s2, 3d, 1, 2, 3, 4, 5, 6, 3d6. And so if we're going to make iron cation, what I'm trying to say up here is that electron does not come from the d orbital, it comes from the s orbital. So 4s1, 3d6. Seems weird, doesn't it? But that's the way it goes. Okay. What if we make iron 2 plus? Argon core. That first electron comes, it's the first electron that comes from the s orbital. So this would be 4s1, 3d5. And then iron 3 plus is argon, and then this is just 3d5. So you can look at this and kind of say, which is the more happy ones on iron? The ones with half-filled subshells, and here we have a half-filled subshell of a 4s1 and a 3d5. So iron 2 plus is a really nice one. And then here we've gotten rid of the 4s shell completely, and we have a 3d5. So iron 3 plus is a really nice electron configuration. And what are the common ions for iron? The 2 plus and the 3 plus. We rarely see iron 1 plus. And so the resonant chords of these electron clouds on the cation are playing a role here in lowering the energy of the system. And so iron 3d5, iron 3 plus is a really stable cation. Now, I talked about the F block and how crazy it is. So here's what I would write out for the electron configuration for mercury. So let's look at mercury up here. You see it's down there at the bottom on row 6. Okay, so I would do xenon core. Does everybody agree with that? That's the previous noble gas. So xenon core. Then we come into the periodic table on row 6. So I should see a 6s2. And then before I get into the D block, I've got the F block. So I've got 4F. I'm all the way past lutetium, which is 71. Mercury is 80, right? So we go all the way past 71. So that is 4F. How many? So there's 10 in the D block. There's 14 in the F block, because there's 7 f orbitals. Each holds 2 electrons. Let's just work that one out. So we'll do it. Xenon core, so mercury. Xenon core. 6s2. And then we get to the 4f. Remember, there's 7 orbitals. Let's just do this from scratch. So what is the angular momentum quantum number for F? So I go S, P, D, F. So I've got 3. L equals 3. So L equals 3. M sub L equals minus 3 all the way to +3, containing 0 in between. Okay. 3, 2, 1, 0, 1, 2, 3. See all of those? Okay. -2. That's a -2. And so how many is that? That's 7, right? 2L plus 1 equals 7. So there's 7 f orbitals. Each of those has 2 electrons in it. So there's 14 total electrons I could put in the f block. So it's 4f14. If you don't want to redo all of that stuff, you can just count all of them. 1, 2, 3, all the way across, and you get 14. So 4f14. Because we're all the way past lutetium. And then we get into the D block. Now I'm on row 6, so that means that's 5D. It's one drop down, so 5D 10. Okay. Now they don't have to be in this order, but that's the order that I do them because that's the order in which they see them in the periodic table. So this is from the Atomic Spectral Database on the NIST website. They have the 4F14 first, the 5D10 second, and the 6S last because the S electrons are what's going to be ionized. Okay, that's what I'm just saying here. The first electron, first ionized electron comes from the S orbital. So that's why NIST writes them last. Okay? But if I were to ask you to write out the electron configuration for mercury, the implication is you're writing it for the ground state. So all of these that we're talking about, the neutral atom, we want to write out the lowest energy electron configuration. I would count that correct because that's following our rules. Okay? But nature doesn't have any clue about the rules. All right. And when it gets that big, the electron energies, again, are so close together, you might get another electron configuration that's actually lower than this one. And there's actually 4 that are lower than this one. Look at this crazy thing. So I still have the 4F14, the 5D10, but I've got a 6S1, and then that last electron is hopped over to the 6p orbital. The 6p orbital, the thallium. Okay? So the 6s has jumped over to the 6p. Why? Well, if it's in the s orbital, it's sharing an orbital with another electron. If it hops over to the p, it has an independent view of the nucleus. So that's one way to maybe conceive of that. So this is the ground state electron configuration. Am I going to ever expect you to memorize or know that? No, you have to look it up. There's no reason why I would expect that that would be the case. Okay, so I'm just having you follow the rules with the few exceptions that we have. So help me decide on what are the exceptions that we're going to enforce, right? So what is the exception I really talked about right at the beginning?
You're looking at D4.
Yeah, it was the D4 group. So chromium, living and constant will steal an S electron and become D5. Okay? The D9 group, they're D9. They're one away from D10, so they'll steal an S electron and become D10. So we'll have something S1, something D10. So those are the 2 exceptions that I want you to know. Okay. The ones with mercury having an S electron jump to the P, I wouldn't have gotten that either. Okay, but I look on the NIST website and it tells me there's lowest energy electron configuration, and I say, okay, that's what experiment tells me. Great. It's a big atom. Again, that's why Simba's warned, don't go there. Okay, just go look it up. All right, you're not going to be able to come up with the hard and fast rules for those larger atoms. Yes. The first exception was the D4 group, chromium, the chromium group. When they're at D4, they'll go ahead and steal an S electron. So it's something S1, something D5. Okay, so we can get half-filled D orbital and keep a half-filled S orbital. And then the D9, which is the copper group. So everything below copper, copper, silver, and gold. Now, what's happening when something tarnishes? Oxygen is coming to that metal and it's stealing an electron. And so if you have something with a really stable electron cloud, it doesn't want to be ionized and it's resistant to reactivity with oxygen. So look at all of these beautiful metals right here. These are very hard to oxidize. Silver, mercury, and gold are noble metals. They don't want to give up their electron to oxygen. And it's because of the electron configurations. They're stable as they are. The noble gases, they have completely filled electron clouds, very stable. They don't want to ruin that cord that they've got going. With all of those electrons oscillating around their nuclei, they're very happy. And so they're resistant to reactivity. And so I'm just, okay, that's great. Any more questions? Because that was a good question. Anything else that I could clarify? Does it help to think more of the cloud as a ringing system? The musicians in here? Okay. For those of you who are not musicians, go listen to like our symphony and listen to and then go listen to like the middle school band. So the symphony is like a noble gas. The middle school band is like maybe an alkali metal, right? It wants to react. The chord isn't just right. Okay, so no shade on the middle school. They're learning. Okay, but yes, I was there once. I played trumpet. So. Yay! I was in the Longhorn band. It was great. Get to go to all the games.